Good morning. So, today we are going to see how to implement the second program in the Visual Computer Graphics and Visualization Lab VTU syllabus. Okay, the program statement is create and rotate a triangle about the origin and a fixed point. So, what is it that we are going to do? We are required to do. We will first draw a triangle. Then we will take the input from the user, whether he wants to rotate it about the origin or the fixed point. Now, suppose he takes about the origin, then we will rotate this about the origin. Okay, that means the angle, this point, if you take, okay, that will be rotated by 90 degrees and we get this. Okay, this point would be rotated by 90 degrees about the origin and we get this. Okay, this point again would be rotated by 90 degrees and we get this. So the resultant triangle would be this. Sorry. Okay. Now, suppose it is about the fixed point, then we take the fixed point and we just have to rotate the triangle. Okay. Now, before we go into this, we will first see the basics. Okay. So, say this is our original triangle. It will get rotated. Now, as you saw, it is going out of the first coordinate. So we will use a viewing window such that we are able to see this also. Okay, so our viewing window is to be defined such that the ones which go outside is also to be made visible. Okay, so we have to select a viewing window suitable for that. Now, what is rotation of a point about the origin? Suppose we have the point P given by the coordinates x comma y. Then if we rotate this point by an angle theta about the origin, then the point P gets transformed to the rotated point P dash. Say the coordinates of the point P dash are x dash, y dash. Okay. Then the rotation matrix we know for rotation about the origin is given by r theta equal to cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. And the point P can be represented by the column vector x, y, 1. Then the point P dash can be represented by x dash, y dash, 1. Okay. So now the rotated point P x dash, y dash, 1 can be obtained by the multiplication of r theta and P. That is cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1 multiplied by x, y, 1 gives us x dash, y dash, 1. That is your x dash equal to x into cos theta minus y into sin theta, and y dash equal to x into sin theta plus y into cos theta. This we already know. Next, what about rotation of a point about a fixed point? Okay, say our xr, yr, that is this point is the fixed point. Okay, then to rotate this triangle about this, what we have to do is, say this vertex will be rotated by an angle theta about this point. Okay, so this angle is theta. So if you're going to rotate about this XR, YR, this vertex, you will get this. Okay. Now suppose you rotate this vertex about XR, YR, then this angle that is made should be theta. Okay. So this rotates by theta. Same way, this vertex, when it is rotated by theta about XR, YR, that means this line should be theta. So this triangle gets transformed into this triangle. Okay. So that is rotation of the point about the fixed point. Now how do we get the coordinates of this rotated point? The point that is rotated about the fixed point. Okay. Now we don't know the rotation matrix. So R theta is rotation about the origin. We don't know the rotation matrix for rotation about the fixed point. So what we do is we translate this point XR, YR to origin. Okay. So we translate the object such that the point XR, YR falls on the origin. Okay. Then we know rotation about origin. So we rotate it by the required angle about the origin. Okay. Now we don't want XR, YR to be here. It should be back to its original position. So once again, we translate it back to the position XR, YR. Fine. So this is the concept behind rotation of a point about a fixed point. So we see that a two-dimensional rotation about any pivot point XR, YR can be generated by performing the following sequence of translate, rotate, translate operations. First, translate the object so that the pivot point position is moved to the coordinate origin. Rotate the object about the coordinate origin. Then translate the object so that the pivot point is returned to its original position. Okay. So given these sequence of transformations, the composite transformation matrix can be obtained by the concatenation of these three transformations. Okay. We know that to create the composite transformation matrix, the first transformation that we write is the last transformation that is performed. Okay. So translation to the original position is T XR YR. Okay. Then that is multiplied by rotate the object about the origin, that is R theta. Then translate the object so that the pivot point is moved to the coordinate origin. Okay. So from XR, YR, you have to move to the origin. That is given by translation by minus XR minus YR. Okay. So minus XR, translation by minus XR minus YR is equivalent to the inverse translation of XR YR. So we know that the transformation matrix for T XR YR is 1 0 XR 0 1 YR 0 0 1. R theta we have seen, and T of minus XR minus YR is 1 0 minus XR 0 1 minus YR 0 0 1. When we multiply these three matrices, the resultant matrix is this. Okay. So we can draw the required triangle and translate it and rotate it about a fixed point either using this. Okay, that is performing the sequence of transformations or by directly applying this transformation matrix. So what we are doing in this program is we will directly apply this overall composite transformation matrix. Fine. Yeah. So the program, first we have the header files. Okay. Include gl/glut.h because we are writing a OpenGL program. Next mat.h because in the rotation matrix you have cos theta, sin theta. For trigonometric calculations you need mat.h. Next, these are the global variables that we declare. Okay, this triangle T33. Okay, this gives you the coordinates of the triangle. Okay, so your vertex point, this is coordinate 10, 10. This is 20, 10, and this is 20, 20. Okay, so the first array gives you the x coordinates. Okay, 10, 20, 20. The second array gives you 10, 10, 10. Okay, and the third array gives you 1, 1, 1. That is corresponding to the homogeneous coordinates. Okay, so those, the T defines the triangle for you. Okay, next you have RT, that is the rotation matrix. Okay, so the transformation matrix, okay, we are initializing it to all zeros. The resultant matrix also we are initializing to all zeros. Okay, now the fixed point about which we rotate, we are fixing. Okay, so we are going to rotate the object about 20, 20. That is XR, YR 20, 20. That is this point. Okay. Now TH gives you the angle in theta, and CH is the variable that we use to collect the choice from the user, whether we are going to rotate it about the origin or about the fixed point. Okay, so first we define all the different functions that we have. Okay, we need a function to multiply. So this function multiply is going to multiply the two global variables, result RES matrix and the RT matrix, the transformation matrix. Okay, so sorry, the resultant matrix is going to be RES, and that is going to be the result of multiplying RT and T. Okay, so we know from mathematics, if you have a matrix A defined by A11, A12, etc., AMN, and matrix B defined by B11, B12, etc., BNP, then the product of the two matrices C equal to AB is given by sigma K equal to 1 to N Aik Bkj. That is Cij equal to sigma K equal to 1 to N Aik Bkj. Okay, that is what is done here. Okay, your A is RT, B is T, and C is RES. Okay, so first this is initialized, RES of Ij equal to 0. Okay, and then this sum is done, okay, by this for loop. Okay, so that is our multiply function. Next, we see the function rotate about origin. We know that the transformation matrix R theta is given by cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Okay, so we assign these values to the matrix RT. That is a transformation matrix. RT 0, 0 is cos theta, cos TH. 0, 1 is this one, minus sin TH. And 0, 2 is this. 1, 0 sin theta, that is this. Cos theta, cos TH is corresponding to cos theta, 0, 0, 0, 1. Okay. Now, once you do this transformation, you have to apply it to the point. That is why you are multiplying. Fine. So this will be the function that will be called if you select rotate about origin. Okay. Next, if you select rotate about fixed point, then what should you do? We have just now seen that the composite transformation matrix to rotate the point about the fixed point XR YR by an anti-theta is given by this. Okay. So this value that you have here, XR into 1 minus cos theta plus YR sin theta, is defined as M. You can see M equal to XR, okay, XR into 1 minus cos theta, so into 1 minus cos TH plus YR into sin theta, so plus YR into sin TH. Similarly, this value, okay, YR into 1 minus cos theta minus XR sin theta is N. Okay, then we assign the rotation matrix or the transformation matrix by these values. So RT00 is cos theta, RT01 is minus sin theta, RT02 is this value, that is nothing but n. Okay. Now RT10 is sin theta, so sin th. RT11 is cos theta, cos th. RT12 is this value, that is nothing but n. RT20 is 0, 21 is 0, and 22 is 1. Then we have to apply the point, so we multiply. So at the end of this, the resultant matrix will contain the transformed point. Next, we have to draw the triangle. Okay, the triangle is we have defined by the matrix T. Okay, so T00 is at T10 will give the first point, T01, T11 gives you the second point and the third one. So we are using GL line loop for this. Okay, so we have GL line begin and we give the 3 vertices. Now for each of the vertices, we are giving a different color. So the line will be drawn. This first point is red color and this is G, green color, and this is blue color. Okay, so the line that you draw will have a graded color. This, excuse me. So when you draw this line, this end is red color and this end is green color. So the line will be drawn in, will be gradually changing from red to green and so on. Okay, so that is how your OpenGL is doing. It is a smooth gradation of colors. Okay, now to draw the rotated triangle, the rotated vertices are available in the matrix RES. Okay, so we use those vertices and draw this rotated triangle. Yeah. Now this display triangle is the display func callback function. Okay, so this is the one that will be drawing our figure on the screen. Okay, GL clear, GL color buffer bit. Okay, this clears the color buffer. If the choice is 1, that is rotate about origin, then we draw the original triangle, we rotate it about the origin, we draw the rotated triangle. Okay, next, if the choice is 2, we draw the triangle, we rotate about fixed point, we call this function now, and then draw the rotated triangle, GL flush. Okay, now what are the initializations? GL clear color, this is to clear the screen to white color. GL matrix mode, this is for viewing. We saw that if we rotate by 90 degrees, we are going out of the first coordinate. Okay, so in order to view, we have to view the entire region. So that is why we are using GLU ortho 2D minus 50, 50, minus 50, 50. Okay, so the negative coordinates are made use for that. Okay, then so in order to define the viewing matrix, we have to move from the model view matrix to the projection matrix. So we do that by GL matrix mode, GL matrix mode, GL underscore projection. So before we set the values to it, it first should be first loaded by identity matrix. So GL load identity, then you have GLU ortho 2D minus 50, 50, minus 50, 50. Okay, so this defines my viewing window. Now coming to the main function. Okay, so printf rotation. Okay, it gives you the choice 1 and 2. 1 rotation about origin, 2 rotation about a fixed point. Okay. Next, it asks for the choice, that is read in the variable ch. It asks for the rotation angle, which is read in the variable th. Okay, of course, here the user will be entering in degrees. So whatever is entered into degrees is converted into radians here. Okay, 3.14 is pi. So pi into pi by 180 will give you the angle in radians. Okay, GLUT init will initialize the GLUT system, OpenGL system. Next, you have GLUT init display mode. Okay, we are not using any animation, so GLUT underscore single, and only a single color buffer is used, and then we are using the RGB color system, GLUT underscore RGB. The window size we are defining as 500, 500. Then GLUT init window position, okay, we are positioning at 0, 0. That is the top left corner. Then GLUT, this creates the window using the previous commands: init display window, init window size, and init window position. Next, we have GLUT display function, that is display. Display is the callback function. So this calls it back, draws the triangle, calls a function to draw the triangle. This initializes GLUT main loop to put the whole thing into an infinite loop. So when you execute, you get this screen. It asks, it gives the choices and asks you for the choice. I have selected one, rotate about 90 degrees. So you see that this is the original triangle that is rotated by 90 degrees, and it is drawn. Because you have used a suitable viewing window, you are getting it in this position. So basically this would be your coordinate system, or your x-axis and y-axis. And so when you rotate, you are getting it like this. If I select the second choice and I rotate by 90 degrees, then the fixed point is 2020. Okay, that is this point. Okay, so this is my original triangle. And this is my rotated triangle. You see that this point 2020 remains fixed. So this completes our implementation of the second program, rotation about origin or rotation about a fixed point. Thank you.